This is problem 3 from chapter 16 of the textbook Stats Modeling the World, 2nd edition. So with this problem, what we're doing is we're playing a little game. It doesn't cost anything to play the game. That's kind of nice. And then what we're doing is we're randomly pulling a card from the deck of 52. So we're assuming it's a shuffled deck. So what they want us to do first is create what's called a probability model. Okay? So what we do for a probability model is it's nothing more than a table of outcomes. So let's call X our outcomes. So X can take on several values depending on what happens. So let's take a look at what they gave us. If you get a red card, you win nothing. Okay, so our outcome is going to be the amount of money that we win. Okay, so we're going to win $0. That's one outcome. Okay, so you can kind of sometimes you kind of think of it as two outcomes, but it's like this is going to be red, so 0. Okay, and then what we want to do for each outcome is say what's the probability of that outcome. So the probability of getting a red card is 26 because there's 13 hearts and 13 diamonds, so it's 26 out of 52. Okay, now it says if you get a spade, you win $5. Okay, so that's nice. $5. And the probability of a spade is there's 13. There's 13 cards, or 13 cards for each suit. So 13 out of 52. Okay, and let's see. For any club, you win $10. So that's nice. And that would be 13 out of 52. However, you get an extra 20, so $30 if the club is an ace. So this would be club and ace. Okay, so there's only one of those cards, 1 out of 52. And so this is sort of be like club and no ace, or not an ace. So there would be 12 out of 52. Okay, so this is called a probability model. Just modeling the outcomes and their associated probabilities. Now we want to find the expected value if we play that game. So the expected value for what's called a random variable like this, discrete probabilities or discrete outcomes. We also use a notation, the expected value of x. So mu is one notation, so the mean, or the expected value of x. That's just the sum of all the outcomes, okay, times the probability of the outcomes. So that's just going to be 0 times 26 divided by 52. 52. I didn't like the looks of that. Let's just start all over. 0 times 26 over 52 plus 5 times 13 over 52 plus 10 times 12 divided by 52 and plus 30 times 1 over 52. Okay, so you can just punch that up in your calculator and you should get $4.13. Okay, so this next question, how much would you be willing to pay to play this game? Well, if you want to win, you don't want to pay more than $4.13 if you do. So this would be per game, right? Per game. So you would probably want to say no more than $4.13 if you play many games, because this is over the long run, right? Over the long run. But if you're only going to play a few games, then probably less. Maybe much less, or more. I don't know. Much less than $4.13 if you are only going to play a few games. Okay? Because remember, we weren't told that it's normally distributed, but if it was, we would expect on average to win $4.13, but there's going to be variability. Speaking of variability, what's the standard deviation for this situation? Okay, so the variance, let's start with the variance and then we'll just take the square root. So the variance is the sum of each outcome less the mean that we just commuted, and we square that puppy, and then we multiply that by the probability of that outcome. Okay, so the first one was 0 and then minus 4.13 squared times, and I believe it was 26 out of 52. So that's the first outcome. Then the next one was $5. So 5 minus 4.13 squared times the probability of getting a 5, and I believe that was a spade, so 13 out of 52. Plus, and then I think we won, what was it, $10? $10, and then 30. Okay, so 10 minus 4.13 squared times 12 out of 52. And then finally, plus $30 minus 4.13. So this is the biggest difference. Square that. But when we multiply it times a small number, it's not going to have this. So you need to punch this up on the calculator, and what I get is approximately 29.5396. So the standard deviation would be the square root of 29.5396, and that turns out to be approximately $5.44. So now you can kind of see, if you played this game, you can kind of see it's a, what is it, $5? So that's like 9, 14, 19. So you're kind of out here. 3 standard deviations is $19. So if you could win quite a bit, but then you could also lose quite a bit as well. All right, so that's how you do this problem. Again, don't start applying this model until you're told. If you're told that it can be approximated by a normal model, then that's different. But I just wanted you to understand where the mean and the standard deviation are sort of why they're useful. Okay, good luck with this problem, this type of problem.